And finally, we reach one of the most famous theorems in probability called the central limit theorem. And that is the topic for today. Now, I highly recommend before you watch the rest of this video that you actually jump over to the video linked here done by 3 Blue 1 Brown. He does an excellent job of giving you some intuition visually and through simulations about all the interesting things that go into this theorem. So take a minute now and jump to that video, and then you can continue on in the slide deck. So what does the central limit theorem say? Its beauty is that no matter what population you're drawing a random sample from, so here are 2 different random populations here. If you take a random sample of size n, and that sample is drawn such that it is IID, so think of sampling with replacement, then as your sample size gets larger and larger, the distribution of the sum of those IID random variables is going to approach a normal distribution. And in fact, I can tell you exactly what the mean and the variance will be for that normal distribution. Now, since sums are a huge part of calculating a mean, it turns out we can also apply the results of this theorem to understand the distribution of a sample mean. This says that my distribution of my sample mean, as long as n is large enough, will also be normally distributed. And we already saw in the last video that the mean and the variance for the sample mean will be given by mu and sigma squared over n. But the new piece that we're adding is that we now can also tell you the shape of the distribution. It's going to be normally distributed. Now, fun fact is proportions. We think of a sample proportion, the number of people you sample who are in favor of some outcome. That can be thought of as a mean if you record their preferences as either 0 or 1. 0, they're not in favor. 1, they are in favor. If you take the mean of all those 0s and 1s, that's equal to the proportion of people who are in favor. So this central limit theorem is going to apply for both means and proportions when we're using those as our statistics or our estimators. Why is this so useful? Well, really, this is a theorem that's providing a sampling distribution of a statistic where we don't need to know the distribution of the population. And we rarely know a lot about the population. So this is gold to have this theory. Let's talk about some of the requirements, the IID and the n going to infinity, how we can make sure that we're satisfying those in practice. So how do you know if your sample is IID? We had a video on this earlier, but if you use a random sample with replacement, that is going to give you an IID sample. Or if you use a simple random sample and the size of your sample is less than 10% of your population size, it'll be close enough to approximate as IID. Okay, now how do I know if n is large enough? Because that's the other criteria here. It really does depend on the shape of the distribution of the population. I'd say a common rule of thumb is you need n to be at least greater than 30. It's possible that you could satisfy, like you can get a sampling distribution of your mean looking very normal like this, like a nice bell shape and predicted well by the central limit theorem, even with as few as 20 for your sample size. But if your population is very skewed, you might need even more than 30. So when in doubt, you can use a technique called bootstrapping to peek in on the shape of the sampling distribution of the mean before you make any assumptions as to whether or not the central limit theorem holds if you have enough n or large enough n. And we will be covering bootstrapping in a future lesson. Let's go back to this demo and think about what the central limit theorem implies in terms of this demo. It means I can make this distribution look as wacky as I want. And if I would like to see the distribution of the sample mean, so again, let's do n is 5 and then n is 25. I know no matter how crazy this looks, my distribution of my sample mean is going to be bell-shaped for large enough n. So we'll see if it works here with n only being 5. It still worked with n being 5. And then notice the difference between n being 5 and n being 25. We would expect that the center of this bell-shaped curve in both n is 5 and n is 25 to be the same as the actual mean, so it should be right around 16.46. But what would we expect the standard deviation to be in both of these scenarios? I'm going to draw a bell curve here and one here. They're both going to be centered around 16.46, but what will their standard deviations be? Take a minute before I run the demo and make your best guess. All right, let's get to work here. I'm going to start doing it in groups of 5, and then we'll go to 10,000, and we'll go to 100,000. Okay, so how did we get 3.9 for this one and 1.75 for this one? We know that the standard deviation is going to be the standard deviation of the population, 8.76, divided by the square root of n. If you do 8.76 divided by the square root of 5, you will get 3.91. And we know for this one, I will get 8.76 divided by the square root of 25. That will give me the standard deviation of 1.75. So if I would like to be more accurate in guessing the actual population mean just using a sample, I need to pick a large enough sample size so that I can get my standard deviation of this distribution to be as narrow as I want within my whatever seems like acceptable tolerance for me. And we'll practice with actually calculating those values here. This will help me decide how big of a sample I need to take to be within a certain level of accuracy. Now, I did this again with this weird one, but I can do any distribution here. So if I clear these, and I really recommend that you do this, just start playing with it and you're going to see, oh, there goes that normal curve again. I can also do very skewed, do the same thing, and there comes my normal curve again. So it's pretty amazing. And granted, my central limit theorem, usually with a sample of size 5, and even sample of size 25, I'm not guaranteed to get a perfect bell-shaped curve here. Really, we're wanting at least a sample size of 30 to see the central limit theorem really kick in. But you can see even here, depending on what your original distribution looks like, that it may kick in earlier. I think if you have like super skewed, like let's see if we can try to break it, you might not get, yeah, see how there, like n equals 5 was not great for a perfect normal distribution, but 25 really seemed to work fine. So this is the beauty of the central limit theorem in helping us know everything we could ever want to know about the sampling distribution of means. So I want to just go back to this idea of the 3 different distributions we've been focusing on and really reiterate what these results imply about these distributions. So if we start again with our population distribution, here I have incomes in dollars. This is just some random data. This has its own mean, it has its own standard deviation, right? Typically we're using sigma to denote the population standard deviation. Then I take a random sample. So this is an IID, I'm doing a random sample with replacement of 100 incomes from my original population. I now get a sample mean and a sample standard deviation. My sample mean here in green is a good estimate of my population mean. And similarly, my sample income is a good estimate, or excuse me, my sample income standard deviation is a good estimate of my population standard deviation. Finally, I have a distribution of sample means. So I repeat this process over and over and over of drawing samples and calculating this mean, and then I get a distribution of all the possible means. That's my sampling distribution of sample means. Now, the mean of this distribution we can show mathematically will exactly equal the population mean. So that's amazing because it's an unbiased estimator. And the standard deviation of this distribution here will be related to the standard deviation of my population. It'll be that standard deviation divided by the square root of n, where n was the sample size. So that here is n. Let's put this into practice. So suppose I tell you a population distribution has an average of 70 and a standard deviation of 10. One of the histograms below is the distribution of the averages of 10,000 random samples of size 100 drawn from the population. Which one and why? Take a minute. All right, so here's the beauty of the central limit theorem. I don't know what the population distribution looks like, so that's unknown. All I know is its mean and its standard deviation. But that's all I need to know thanks to the central limit theorem, because I can say by the central limit theorem, the sample mean, and we're doing this now, samples of size 100, is going to be, so that's my distribution notation, it is a random variable that's normally distributed. It has the same mean as the original population, but its standard deviation is going to be the original population's standard deviation divided by square root of n, which means that the variance, because that's what we normally put here, the variance is going to be the population variance divided by n. Okay. So this means I'm looking for which of the following is a normal distribution centered at 70 with variance equal to 1, which means the standard deviation is equal to 1. So all three of these are centered at 70, so that doesn't help me. Now I need to eyeball the standard deviation. So remember the fun fact that the standard deviation is going to occur, if I look roughly where my inflection point is on this curve, come down here, that occurs one standard deviation away from the mean. So I would assume this is 1 standard. And again, the standard deviation of a statistic like this, which where you're doing a statistic, we're using these sample averages, is called the standard error. So 1 standard error here would be 10. So I notice here that my standard error is approximately equal to 10 here. My standard error is approximately equal to 1 here. And my standard error in this one, I would eyeball it's happening right around here. Standard error is approximately equal to 2. And standard error is my square root of the variance, which is your population standard deviation divided by square root of n. That's the same as the standard deviation of the distribution of the statistic. In this case, the standard deviation of the sampling mean. Okay, so out of all, that is a long way to say that B is our best answer here, because we were looking for which curve was centered at 70 and had a standard deviation of 1. Let's try another one. Suppose salaries at a very large corporation have a mean of 162,000 and a standard deviation of 32,000. If a single employee is randomly selected, what's the probability that their salary exceeds 175,000? And then if 100 employees are randomly sampled, what's the probability that their average salary exceeds 175,000? Give this one a shot. All right, so part A, again, to think about what you need to calculate a probability, I need to know how X is distributed. Let X be the salary of a random employee. Salary of employee. X is distributed how? I don't know. So then to be able to say what's the probability that X is greater than 175,000, I don't know. Not enough info. Because I don't know the probability density function. Not enough info here. Just because I know the mean and the standard deviation doesn't tell me what that probability density function is. It could look something like this. It could be uniform. It could be a bimodal situation. I could make PDFs that all have the same mean, the same standard deviation, and look wildly different. So I can't calculate an actual probability here without knowing something about the distribution of the salaries, and I was given nothing. So is that also the case in B? Well, B, now I'm interested, I want to know their average salary. So now I'm interested in the distribution of the sample average of a sample size of 100. And this is where the central limit theorem can come into play. Let's make sure that our criteria holds. The central limit theorem, let's see if it's going to hold. Can I assume that I have IID, so central limit theorem, I need IID and I need n to be large. So n greater than 30 at least. N is 100, so that's great. IID, so I wasn't told whether or not this was sampled with or without replacement. If this was sampled with replacement, then for sure I could assume IID. If it was sampled without replacement, I would need to make sure that 100 was less than 10% of the total population. And because I said very large, I think that I'm safe to assume that whether or not this was with or without replacement, this will satisfy the criteria to be IID. So we need IID, n greater than 30, and then we need to be either trying to look at sums or means, right? We're looking at the sum of random variables. Okay, so that means this all applies, which means I now know the exact distribution and I can calculate the exact probability. The mean of this is going to be the same as the mean of the population, so 162,000. Now I need to think of the variance. So the variance is going to be the variance of my original population, so 32,000 squared divided by n, and I had n was 100. Okay, and now I want to know what's the probability that this random variable is greater than 175,000. Okay, I can definitely just pop this into Python. So notice when I pop this into Python, so basically I have a normal distribution. I want the probability that it's greater than this value of 175,000. So I'm going to do 1 minus the CDF. So I want to do 1 minus stats.norm.cdf. I'm putting in 175,000. My mean is 162. Then remember, the trick is that the input to stats.norm, this needs to be your standard deviation or your standard error here, not the variance. So that's why I did 32,000 divided by 10. So I'm going to have 1 minus 0.99975, which is approximately 0.00002. So very tiny probability that their average salary is going to exceed 175,000. So what's amazing, again, to bring back to light is I didn't need to know anything about the actual population distribution for the salaries, and I was still able to answer questions about the probabilities of their sample mean. All right, let's do another practice. So take a minute, read through these, and decide which of the following are true and which are false. All right, no matter what population you're drawing from, the sample distribution is roughly normal. That is false. The sample distribution should look like the population distribution that you're drawing from for a large enough n. No matter what population you're drawing from, the sampling distribution of the sample mean, that is true using the CLT. And again, we're assuming that your sample is with replacement here. Or if not, that you have a small enough proportion compared to your population so that we can make the IID assumption. No matter what population you're drawing from, the sample distribution of the sample median, no. So this is false. The sample median cannot be written as a sum of independent and identically distributed random variables. So the central limit theorem won't apply for it. And we saw that in our demo in the previous video because we looked at the sampling distribution of medians. It wasn't bell-shaped necessarily. All right, let's do this in groups of 5. Okay, so if I keep going, go to 10,000, 100,000, aha, okay. But I still have an interesting like this bimodal thing happening. Okay, last one. If you're drawing from a Bernoulli distribution, the sampling distribution of the sample proportion is roughly normal. So you have to think of what you mean by the sample proportion. If I'm drawing from a Bernoulli distribution, I'm going to be getting a bunch of zeros and ones, 0, 1, 0, with whatever, probability I have underlying this distribution. The sample proportion in this case, I have to pick I'm either looking at the proportions of zeros or the proportion of ones. Either one's fine. So let's assume I mean sample proportion of ones. Right, so I want the total number of ones divided by the total in my sample. And if you notice, that sample proportion of ones is the same as the sample mean. And we know, thanks to the central limit theorem, that if I have sample means, that is going to be normally distributed. So that is true. So while this is the end of this video, this is not the end of where we'll be using the central limit theorem. It will continue to show up throughout the rest of this class.